Hi, I'm George Hammond, conference producer at Technology Networks, and I'm here to introduce the final talk of the day, Opportunities and Challenges of Aqueous Metal Batteries. I'm incredibly pleased to welcome Professor David G. Professor G is the Bert and Emmeline Christensen Professor of Chemistry at Oregon State University. His research interests pertain to the design principles of battery chemistry for energy storage. He obtained his BSc in chemistry from Gillen University in 2003 and PhD in chemistry from the University of Waterloo in 2009. He has been a highly cited researcher of the Web of Science group since 2019, with total citations of over 37,000 and a H-index of 85. A very warm welcome to you, Professor G. Following the presentation, we will also have a Q&A session, and we welcome any questions you may have. Please ask questions using the Q&A system to the right-hand side of the video player. And now, without further ado, I will hand over to Professor G to begin his presentation.
Thank you, George. Thank you for the kind introduction, and I'm grateful for your kind invitation from the Technology Networks. So today I will talk a little bit about aqueous batteries, the big picture and some detailed scientific problems and our solutions. So, so I want to actually talk about how we get energy, where we get energy, and how we use it first, because this is most relevant why we need a storage in the first place. So if we look at the solar and wind, they are doing really well in the recent several years, in the last maybe last decade, from nearly nothing in terms of the energy percentage, now to 15% of the total electricity generated for the United States. So that's quite remarkable. And we have to know that when the renewable energy, especially solar and wind, they are intermittent. When they are intermittent, that means sometimes they're not so predictable. And when the percentage of these energy sources being above 10%, that is a threshold that we have to be careful for the aging grid, because they can have some heavy burden and the stability can be a challenge. So put that in mind first. And then let's look at all the fossil fuels, right? Natural gas, coal, and petroleum. If you compare the same map prepared by Lawrence Berkeley National Lab for previous years, you're going to notice that natural gas is increasing, and that is replacing coal. But in total, the uses of fossil fuels is actually decreased, but not by a lot, right? So a few years ago is 80%, now it's almost 79%. So what is the challenge for intermittent renewable solar and wind installation to further increase? The challenge is the storage, right? If you don't store it, the grid will be heavily challenged, right? So now let's move on to storage. So this is not so much in the radar of the industry until a few years ago, actually. So it's going to be a huge market. Currently, most attention for storage or for batteries has been given to electric vehicles, but in the future, energy storage will probably an even bigger market than transportation. So this is the prediction given by Bloomberg in 2019. So from 2018 to 2040, it's predicted that the market or the installation of storage globally will increase by 100-fold, 100 times bigger. So, well, the annual rate, the growth rate will be 16%, right? So if you look at that, oh, wow, this is 100% bigger. It's quite ambitious, right? Quite optimistic. But the reality is even more encouraging. So this is the real data from 2018 to 2022, and the real growth is 7 times just in 4 years. 7 times in 4 years. The annual growth rate is 63%, right? That's outstanding, right? That's astounding as well. And now, what is driving the increase? So one major way of storing energy has been pumped hydro, right? Pumped hydro is like you raise water to a high altitude and then let it flow down to turn to spin the turbine and to generate electricity. So this is a map published in 2019. It is a simulation and a computation work to predict where you can build more pumped hydro facilities. And there are quite a lot actually, right? It looks great. But if you compare this map with the map of population density, well, this is quite aged 2000, right? So now it looks denser, but a ratio, the distribution remains similar. So if you think about the United States, 80% of the population are living to the east of Rocky Mountains, right? So, but most of the pumped hydro sites are to the west of the Rocky Mountains, right? So for Europe, the entire Europe, right, Northern Europe, Eastern and Northern, is very flat. It's very flat. You don't actually have many good places to build pumped hydro, well, except for the Southern Europe. But the population centers are all over the place in Europe, so they don't overlap. Same thing for China, Eastern China, Northern China is very flat, right? But you cannot build a pumped hydro, but a lot of people are living there. Right? So the good locations are Northern India, right? That is overlapping very nicely, and South America, right? That is overlapping nicely. Right? So, but still, there are a lot of work to do, and pumped hydro just won't solve the entire solution problem. So now let's take a look at the again real progress, right? This is the pie chart for the storage technologies. In 2019, globally, 93% of storage is undertaken by pumped hydro, right? 1 year later, maybe this is 1 year plus, 9 months later, 2020, Q3, and pumped hydro now is lower, right, by 1.4%, 1.5%, right? That's lowered. And lithium ions increased, right? And 2023, wow, that's a big drop of pumped hydro, right? From almost 92% to now 73%, right? For the global energy storage, solutions percentage. Now, if you look at China, it's below 70% for the first time, right? So, and if you look at what is the alternative right now? Well, certainly it's electrochemical energy storage. Usually, that is considered equivalent to batteries, but you also have electrochemical capacitors, but they don't provide a lot of contribution here. So it's mostly lithium ion, right? It's 87 all the way to 96, 95, 94. So my question is, this is not so sustainable. I'll explain why. It looks great, but where are we going here? It's not very sustainable. So this is the scheme for a planned facility for battery-based energy storage farm in UK. This is supposed to be a 1 gigawatt, right, power, and it can sustain power output for 2 hours, right? So it is scheduled to be operating in 2025. So I just want to point out that there are several characteristics you want to pay attention, right? So in the scheme, you can see that it is built on the ground, like one floor, right? And all the battery facilities are, segregated in certain chambers. And I'm not sure this is a coincidence or not. It's built along the river, right? The reason for that is my actually hypothesis is that there might be some safety concerns here. And it is, lithium batteries is known, right? It's known not to be infallible. And the safety concern is due to the flammable electrolyte and the very oxidizing cathode. Sometimes if you use metal oxide, when they are charged to certain high voltage, they can release oxygen and that can ignite the electrolyte. So thermal runaway is certainly a real challenge here. And with the remarkable progress from the industry, the defect rate, is very small. It's 1 in 1 million, right? That's a very small defect rate. But for storage sites, that is gigawatt scale, 1 in 1 million can be an issue, right? So usually they have, tens of millions of cells. So that's one issue, the safety. The second issue is recycling. Have we figured out how to recycle these lithium-ion batteries? Well, the answer is not so encouraging. We have not, right? So at least there isn't a mature industry to address the recycling for all the lithium-ion batteries. Now, what is the future energy storage should look like? Well, this is again my hypothesis. I think we should have the efficiency, right, in terms of volume, in terms of the footprint of the factory or the farm, right? If the batteries are safe enough, they can be shoved with different levels in a building like this is like Costco shelf, right? You have the goods packed up. The batteries should be able to do that. Well, if you want to pack the batteries this way, they cannot be very heavy. Lead acid batteries cannot be packed this way. No shelves will be robust enough to withstand the weight of lead acid batteries. So we need new batteries that are almost infallible, that are very safe. So let's take a look at all the solutions available for energy storage. Oh, this is a paper published in 2011, but it's still comprehensive enough. And now we can use it. So I just talked about pumped hydro. Compressed air is also another primary solution, but it's not widely available because you need some kind of geographical, locations, and in particular, you need salt cavern, right? And that can be sealed, right, to provide the pressure you need to release due to the compressed air to be stored. And if you look at this whole map, right, lead acid has been, that has been there forever since 1859. That was the first secondary battery or rechargeable battery invented, right? And so right now we have a lot of activities with flow batteries. Right? Flow batteries are actually promising, but if you use vanadium, it's going to be a challenge because vanadium is rare, it's toxic, and the price has been volatile, right? So I don't have too much time to explain the challenges of every single technology here, but if we have questions, we can talk about that. So what do we really need is somewhere here. We provide a good, energy density, and that can be discharged and charged at a relatively high rate. And most importantly, it has to be sustainable and the economies of scale should be playable for such technologies. So, and my consideration here is aqueous metal batteries may have a shot there. So now let's take a look at how do we select elements per se for the design of the future batteries, right? There are several tiers of elements we can consider. The first one is Earth abundant, right? These elements are very sustainable, and they are going to be low cost. The more you use them, the more you mine them, the chance is the cheaper they will be. Right? The second tier is these blue ones. Lithium is there, and zinc is there, copper is there. These elements are fine. They are usually produced as a commodity in a large scale, right? So that's workable. So now the following sections, these are too heavy, right? And these actually elements are too expensive, obviously, noble metal, right? And these are too toxic, right? So beryllium, well known, and cobalt is toxic as well. Arsenic, well known, toxic. So the lanthanide and octinide, these elements, they're hard to mine and hard to refine, but the uses of them are not well understood yet. Right? So these are something we have a question mark. And then the natural gas and radioactive elements, chromium is only toxic when it's 6 plus. All right, so we give a preference to the green and blue elements for the future design of new batteries. Now, I just mentioned about the scale of production. These elements in a green region, they are manufactured as commodities, with a large production scale. So, you can see iron. If you can use iron, right, for as a battery, either anode, cathode, it's going to be remarkably sustainable and cost effective. So sodium, the same thing, chlorine, right, and calcium, and zinc is there, and because it's actually is a ore usually coexist with copper. If you mine copper, you most likely will have some zinc produced. So we have a lot of zinc produced, and so even though it's relatively rare compared to other elements like aluminum or iron, but it's produced with a large quantity per year. So we try to actually avoid elements down there, right? Because they are not produced a lot per year. All right, so we just talk about abundancy and whether the elements are there, being earth abundant or being produced as large quantity. Now, in the end, for industry to make a decision where to go, which technology to adopt, it will be about a cost, right? That cost is levelized energy cost, right? So that cost is everything included, maintenance, for example. We just mentioned about the abundancy. That's the capital cost, how much you're going to spend to fabricate, right? The electrodes, the electrolyte, the whole cell, and how to maintain the batteries. For flow batteries, you kind of need to spend some money for maintenance, right? Electricity cost. When you purchase electricity, is that renewable electricity that is low cost or not? For the denominator, we need the denominator, this product, to be as large as possible. Right? So we hope the cycle life to be as long as possible, the energy density or specific energy as large as possible, energy efficiency, right? So it's how much energy you can deliver after you store it, right? So you store 100 watt hour, can you actually get 95 watt hour out of your device, right? That's energy efficiency. And depth discharge. Depth of discharge is notoriously low for lead acid batteries, right? So, but for lithium-ion batteries, often you can discharge to almost 0%, right? You do that all the time, but it's going to hurt the battery, but still, you can do that. Right? So the product of all these parameters, we hope them to be as large as possible. And the numerator will hope to minimize, right? So now, if you look at this radar chart, I want to highlight the difference between the current lithium-ion batteries and the current zinc metal batteries and the desirable features of future zinc metal batteries, right? So for lithium-ion batteries, the cost is high, is well known. It's not very sustainable, either from the lithium point of view, or if you use nickel and a cobalt, right? 2035, we're gonna have shortage of cobalt. 2045, we're gonna have a shortage of nickel. That was predicted from a paper published by Yuxin. So if you actually consider the safety, right? So we use safety as probably the highest priority for the selection of storage batteries. If it's not safe, you cannot pack them up. You cannot actually have the modules, packed to a gigawatt, right? So that is a must for storage batteries, and lithium ion is challenged there, right? Lithium ion is challenged there. So for the current zinc metal battery, why the cost is not so good? The reason for that is the cycling life. The cycling life of the current zinc metal batteries is not very long. right? And the reason actually are twofold. One is the zinc metal is not very reversibly plated and stripped, and a cathode is not operating reversibly either. So I will go into the details for the zinc metal part. All right, so for our job, right, for the future, zinc metal batteries, the highest priority is to promote the cycling life, and which is a function of the reversibility of the electrode operation. For the zinc anode, it is about how reversible you can take a layer off the zinc metal after you plate that layer, right? So that is the stripping over plating efficiency. All right, so the aqueous batteries is a very diverse field, right? Is a vast field. It's not just a zinc battery, and currently activities exist for iron batteries. My group also work on iron batteries. I think that might be the future. That could be the next generation of aqueous metal batteries to replace zinc. Well, that's probably years later. For high power aqueous batteries, proton batteries and ammonium batteries can be very interesting, but I don't have time to talk about it today. But we did have some result in this area, which is quite interesting. They have a seeding of energy density because they are rocking chair batteries. They don't use metal as the anode. Metal as the anode is the premise for high energy density potentially. If you don't use metal as the anode for aqueous batteries, the energy density won't be very high. So the reason we focus on zinc is due to the potential of high energy density, right? So there are a lot of research, and the sodium ion batteries have been commercialized, right? And but they do have some inherent limit, which is shared by lithium-ion batteries. They use non-aqueous, electrolyte that are flammable. So inherently, I will have some safety concern for these batteries if they're packed into the gigawatt scale. All right, so let's move on to some data. Now, I just mentioned the reversibility of metal anode is a challenge, right? I want to show you what is the root causes for the irreversibility. The number one issue is dendrite. Dendrite is a very vague, generic term. Usually it's describing a morphology that is not so flat, not so smooth, right? It could be, a flower-like morphology, could be like this, plicet-like, it could be whiskers or dendrite. So, but we use dendrite just to make sure we understand each other in a community. Right? So this kind of morphology after plating is not going to be so nice, right? And that's the number one issue. The second issue is hydrogen evolution. Zinc react with water, right? It's thermodynamically, zinc is not compatible with water. So I have actually, iron actually is similar. Iron is similar. I have some video here taken by my collaborator, Dr. Julie, in MIT for iron, right? We have 3 electrolytes here. I want to show you, no, somehow, okay, right here. I want to show you how bad the hydrogen evolution could be. Look at this one, right? If you don't do any treatment, right? And this is how bad the hydrogen evolution could be. It's like a storm, a winter storm, right? We just have been through at Oregon. And so for this one, this electrode, we have treated that electrode with our designed electrolyte, right? Look at that, how peaceful that is. Right? So this is the topic we're going to work on. So I don't have too much time to show you the iron project we have. The papers are being prepared, but I have some data to show you the zinc part. So how do we evaluate the reversibility of metal anode? We use Coulomb efficiency. Coulomb efficiency is how many charges you can reversibly taken away we call it, stripping process. During the stripping process, slash the charges you plated onto the electrode, right? So Coulomb efficiency, if you have a Coulomb efficiency of 95%, that sounds pretty good, right? You're going to lose 50% of your electrode in just 15 cycles. So if you double the capacity of your anode, right, you use twice the capacity of your anode compared to the cathode. 15 cycles later, the excess of capacity from your anode will be gone, right? That is 174 cycles for 97.63%. And if you have a very nice Coulomb efficiency, 99.95%, right? So that battery can last 1400 cycles with 50% of the mass lost for the anode side. All right, so what is the mechanism for dendrites to be formed? So it is related to a well-known phenomenon. It's called a sand extinction layer. So if you have plating going on, your electrode or current collector is negatively polarized. You're going to have an excess of electrons on the surface of the metal. And then that's going to attract cations, and cations are converted to metal. Because the surface is negatively polarized, it's going to repulse the negatively charged anions away. You're consuming cations, you are pushing anions away. You're going to generate a vacuum of ions near the surface of the electrode or the current collector. And then due to that vacuum of ions, any asperities of the surface will be generating high electric field. The electric field will be high because the vacuum here, and then you're going to grow that asperities into whiskers or dendrite, right? That's the fundamental cause for dendrite formation. So in this slide, there are two solutions I want to show you. One is you use extremely concentrated electrolyte. See here, you push the ions away from the surface. Now, when the electrolyte is extremely concentrated, these ions will have nowhere to go because they're going to be repulsed back by the highly dense presence of ions, not so far away from the surface of the electrode, right? So that is one solution, extremely concentrated electrolyte. Another solution is to use so-called ionic screening. So we have two types of cations in the electrolyte. We have our anode cations converted to anode mass metal. We have another type of cation which cannot be converted to metal because their potential is going to be extremely low to be converted to metal. We don't have that low potential for these cations, to be converted to metal. For example, if we plate zinc and we add some lithium ions in the electrolyte, the lithium ions will not be converted to lithium metal. All right. So these cations will be convened on the surface. They'll be here, right? And they don't actually they don't allow the vacuum or the extinction layer to be formed. As we call the ionic screening. And with the cations here, the ions will be attracted not so far away. So these are two promising solutions. Another one is to grow a so-called solid electrolyte interface. This is something that hugely benefited the lithium-ion batteries, and it is arguable that it is due to the solid electrolyte interface grown on the graphite surface that enables the commercialization of lithium-ion batteries in early 1990s. So now, if we have the electrolyte decomposed on a surface of the electrode, and this decomposition layer, this layer is like a mosaic, makeup of some polymers or organic mass converted from the decomposed electrolyte molecules. And also you're going to have some salt formed. These domains of salt will be comprised in the layer. We call it SEI layer. And because you have cations, anions in this layer, guess what? It will not generate that vacuum of ions, right? You won't have the depletion zone anymore. So Bro SEI will be a very effective way to prevent the dendrite formation for metal batteries. Well, but this approach is not well explored yet, right? All right, so another challenge, as I mentioned, about hydrogen evolution, right? Hydrogen evolution is, for zinc, is a thermodynamic phenomenon because zinc is reducing enough and water is oxidizing enough. When they meet, they're going to react, right? So ideally, the potential range should be like this. We have anode operating at a potential above hydrogen evolution. So anode will not be reduced. We have a cathode operating at a potential below the potential of oxygen evolution. So cathode will not be reduced, right? So that's the ideal case, right? And hopefully we have a large, gap between the cathode and anode operation potential. So we call that a voltage, right? 2.5, hopefully. Now the reality is our metal anode is operating below the hydrogen evolution potential. So water can be reduced by the zinc metal, right? And often the operating of the cathode is frustrated by the oxygen evolution. That is because they are close enough. Now, two solutions. One is to move this HER down there, right? So we can and we need to tune the thermodynamic stability window of electrolyte. And then the second solution is to grow solid electrolyte interface to passivate the surface of the metal anodes. And today I'm going to introduce these two solutions to you. Now, talking about hydrogen evolution, what are the pathways for this parasitic reaction to take place? If your electrolyte is acidic electrolyte, you're going to have a lot of protons. So protons will take the priority to be reduced than water. Protons are a better acid than water. So proton will be reduced first. Now, how to address that? Well, the solution is to turn the acid not so acidic, right? To minimize the acidity. Another pathway is you have relatively neutral electrolyte, right? The pH value is from maybe 6 to 8 or 5 to 9. It's not so acidic. So the reductant, the species to be reduced is going to be water, right? You're going to have water to be reduced instead of protons. In this case, there are several solutions introduced by the community. So one is to decrease water's activity, make it less concentrated. And the second is to strengthen the OH bond strength, right? And the third is to decrease the solvation energy of hydroxide. And this actually is less intuitive. I will explain why that's it's gonna be very effective. And we were the first kind of talking about this. All right, so let's decrease the activity of water, right? The solution for that is to generate the so-called water in salt electrolyte. And this concept was firstly introduced by the authors, Dr. Wang and Dr. Xu. So they have a highly concentrated lithium TFSI electrolyte, which is 21 molality, right? It's the molality, not molarity. So in this electrolyte, you're going to have incomplete solvation shell of cations, and water is effectively less concentrated in this electrolyte. So we call it water in salt. It sounds like salt is the solvent, water is the solute. Right? That's the notion of water in salt. Well, there are some issues with TFSI and or fluorinated molecules due to the cost and environmental concerns. So my lab, we focus on since actually 2017, we focused on zinc chloride. So zinc chloride is cost effective and it's not toxic. And most interestingly, if you use different concentrations, the speciation of anions in this electrolyte will vary dramatically. If you have a low concentration of the zinc chloride, the cations course, is hydrated zinc 2 plus. The anions are chloride. But if you turn this electrolyte highly concentrated, the anions now is the tetrachlorozincate, right? That's very interesting. Now, if you have these two ions, it turns out that the lattice energy of this new salt, if you pack them, is going to be lower. So this is a more soluble salt per se. So you can dissolve a lot of that, right? So when you have a high concentration, we talked about it already, it's going to suppress dendrite. And then another interesting phenomenon is you can add other chloride. You can add lithium chloride, sodium chloride, potassium chloride, ammonium chloride, all kinds of chloride into this electrolyte. And these cold salts will be allowed to dissolve. Why? Because the chloride anions will be used to convert more zinc ions to this anion species. And so that allows a lot of cold salt to be dissolved at a high concentration. That's quite interesting. And the third one is this is very important. The third one is probably the most important point here. With this anion, this is a very soft, bulky anion. It is our hypothesis that if you use very soft, bulky anion, excuse me, and then it's going to generate free water molecules. When you have free water molecules, it's going to dissolve hydrophobic molecules. So I won't have a lot of time to talk about that, but just for now, for now you can see that I will show the evidence, and this helps dissolving organic molecules. Very critical. So now for ion speciation. So this is actually the Raman work from my colleague Dr. Chung Fang at OSU. So if you increase the concentration, right? So the species here, this is the highest peak is due to the tetrachlorozincate, right? So this complex ion is here, and you also have some oligomers formed here. That's quite interesting. So this monomer is going to polymerize, right, into oligomers. And we do have some hydrated zinc 2 plus here. All right. So I just mentioned that you have the zinc chloro species here. That's the anions, right? And I mentioned about the screening effect. So the initial motivation to add lithium chloride to zinc chloride is to generate that screening effect. But beyond the screening effect we're going to have, we found that we actually generate a different chemical environment for water in the electrolyte. So again, this is the Raman data. This is actually the femtosecond stimulated Raman spectroscopy. Very sensitive, very sensitive. Now, if you add lithium chloride into zinc chloride by increasing the concentration, it's very interesting. We know that this peak, we found that this peak is shifting to a higher frequency, it's blue shifted. Now, if you look at the water stretching vibration modes, right? This is water's stretching vibration modes. The left side, right? The left side is heavily, hydrogen bonded, and the right-hand side is not so hydrogen bonded. And usually, a higher frequency means a better stability, right? The water molecules, the OH bond is vibrating faster, and that means the bond length is shorter, and the bond enthalpy is higher. So now by adding more lithium chloride, what do? We actually we convert more zinc cations to this complex anions. We generate more of that. And look at this. We have a blue shifted peak for water vibration. It means we strengthen water. We are strengthening water's the OH bond enthalpy by adding lithium chloride, and it's producing more zinc chloro anions. So if you say, oh, I don't think that is very convincing, because if you just add lithium chloride alone into pure water, what's going to happen, right? Maybe just due to the lithium chloride alone. So we did that. We just add lithium chloride to pure water, right? So we make it extremely concentrated, 20 molar lithium chloride. Look at this peak. It's not shifting. It's not shifting. So by having more chloride ions or lithium ions, you are not going to shift this peak. So comparing the two salt solutions, the only difference is that um, we have a lot of zinc tetrachloride here. All right, so by having a concentrated solution, so we actually is producing a higher Coulomb efficiency compared to a low concentration, right? 30 mole now, you get a 95%, for a dilute electrolyte is only 73%. But now by adding lithium chloride, this Coulomb efficiency is even better, 97.6%. And by the way, we use this reservoir calculation method for calculating the Coulomb efficiency. And this was firstly introduced by Dr. Albach. All right, so recently there is a report by having a specific ratio between lithium chloride and zinc chloride by Dr. Chunsheng Wang, and they also observe very high Coulomb efficiency. Now we notice that you can turn the electrolyte more stable by adding whole chloride, right? How about doing that with a soft cation, with tetramethylammonium? A soft cation will not polarize the salt as water as much, so that could reduce the acidity. So now we are talking about acidity reduction. Again, this reaction is going to be very similar. We have a new salt added. It's going to actually deprive, zinc from water and turning zinc to form more zinc chloral species. And now the hydrated cation is replaced by TMA instead of zinc. So this will not polarize water molecules. It will be less acidic. Now, we increased the Coulomb efficiency from 97.6% to 99.6%. And the Raman data shows that the vibration of the hydrated zinc decreased dramatically after we add tetramethylammonium ion into the electrolyte. So for that, we also decrease the acidity. So this is the zinc, purely zinc chloride solution, and that is the lithium added one. So we use a Hammett acidity test. It's not like a regular pH value. You cannot use a pH value to evaluate acidity of highly concentrated electrolyte. So Hammett acidity is more accurate, and you have to use some indicator base to do that, right? To observe by UV vis, to observe the presence of the indicator. The more indicator you can observe, the less acidity the electrolyte is, right? So for highly acidic electrolyte, you don't observe any indicators, right? They're gone, they're captured by protons. But now if you add TMACl, you observe some indicators. That means the acidity is decreased, all right? That's the indicator. So again, the Coulomb efficiency is further increased. Now, I want to actually highlight a new result that we just discovered that by lowering the temperature of aqueous electrolyte. So this is a lithium chloride or a phosphoric acid electrolyte. They can stay as a liquid at very low temperatures. At a minus 70 degree Celsius, they stay as a liquid. Right? So this allows us to test their electrochemical stability window. So by lowering the temperature from 20 degree to minus 78 degrees Celsius, we notice that the window for both electrolyte is dramatically increased. Now we combine the two electrolyte to form this more accurate map of water, because you cannot use the OER side for lithium chloride because chloride will be oxidized. So this is not oxygen evolution, this is chlorine evolution. So we cannot use this part for this electrolyte. Now for phosphoric acid, we cannot use the HER side because it's not about water, it's about protons, right? But if you combine these two electrolyte, then you can provide a whole picture of how water behaves at a low temperature compared to the room temperature and a relatively low temperature. So by lowering the temperature, water becomes a less reactive solvent. It's inert, right? Now, the voltage window for water here is not 1.23, it's actually over 3 volt. Why is that? We started Raman again. And we noticed that after lower the temperature, this section, the lower frequency section is promoted. We know the lower frequency corresponding to a weak bond enthalpy. So we lower the temperature for the whole solution. Water is less stable because the high strength of the hydrogen bonding, that's going to weaken the OH bond of water, right? So this is very, very puzzling. Now, we also test the NMR, right? The NMR also tells us that by lowering the temperature, you're going to have a downfield shift. That is about de-shielding of hydrogen nuclei. De-shielding means you have less electron density around protons, around hydrogen. That is also about a lowered bond enthalpy. So how come, right? How come you can have a weakened water molecules, but you have the aqueous solution, the voltage window dramatically increased? So now we have to look at the entire equation. Water is the reactant. The product is hydrogen gas and hydroxide. Hydrogen gas is leaving as a gas molecule, right? It's not going to affect the total energy of the product much. It's a constant. No matter how you change, you transform the environment of the electrolyte, it's going to be the same for hydrogen gas. However, the hydroxide side will be different. If you have different chemical environment, you're going to have different solvation energies of hydroxide, right? This is the same thing for the oxygen evolution side as well. So if you tune the chemical environment for the product side, this reaction, right, this hydrogen evolution reaction, the potential can be very much different. So that's the conclusion. We have some new result to show that this hypothesis is very, very promising. It's close to what really happens, but I don't have time to talk about it now for the fundamentals, but I can show you by design the electrolyte how dramatic the stability can be, right? This is an aqueous solution. What you're gonna see is we're gonna drop some lithium foil into the aqueous solution, right? This is the most stable aqueous solution we have designed. Look at the lithium foil, quiet, very calm, not exploding at all, right? This is a less stable one. You see some bubbles? This is pure water. That's pure water. That's the electrolyte we designed with the hydroxide solvation heavily frustrated, right? That's going to be something new we will report. All right, now let's move quickly to the kinetic side. After design the electrolyte to be more electrochemically stable or thermodynamically stable, what else we can do? We can grow the ICEI. Let's talk about ICEI. So I mentioned this electrolyte is allowed to co-dissolve some organic solvent. That's what happened, right? So we actually dissolve dimethyl carbonate with our zinc electrolyte. And this is with different ratios. That's water to DMC. Water to DMC, it's basically just miscible. You can use any ratio. It's going to co-dissolve. And after adding DMC, DMC is a weaker Lewis base. It's not going to replace water, or it's a Lewis base than water and chloride. It's not going to replace water or chloride from the solvation of zinc. So you look at this different spectra of, with different DMC added, it's not going to change, right? So that's initially very discouraging for us. So it's like, oh, we're not going to change the speciation of zinc. Then how are we going to affect the performance of zinc plating? So now the next spectra is more encouraging. So we have the DMC OCO vibration. Now that's a vibration, right? And then we're going to have a split, right? After adding two different electrolytes, that means actually DMC is interacting with their neighbors. That is very encouraging. Now take a look at the acidity of our electrolyte, right? So this is the DMC added electrolyte. We have a lot of indicator observed. That means there are few protons who are capturing our indicator molecules. This is very encouraging. So that's the change. So now with the electrolyte less acidic, well, that's one thing to promote the zinc plating Coulomb efficiency. So now we have the Coulomb efficiency of 99.95. This is the goal we have. And that means you can have a zinc metal anode that is reversible for a long cycling of zinc metal batteries. Now, we also used the gas chromatography to observe how much hydrogen gas is produced with different electrolyte. Now, this is the conventional zinc sulfide electrolyte widely used. It's not going to be very stable with zinc metal. It's producing a lot of hydrogen gas. Now, if you look at a peak here for hydrogen gas and the concentrated zinc chloride, you have a bump here, and now with DMC added, that bump is almost gone. So by comparing different electrolyte, so for the DMC is known to be flammable, but if you use a certain ratio, right? So if you use pure DMC, of course, it's going to be flammable. But if you have 1-to-1 DMC, right, with water, like in terms of mass, so it's going to be flammable too. But if you increase water's ratio, so DMC versus water is 1-to-2, then it's not igniting here, right? So our electrolyte is right here. So the DMC versus water is 1-to-5. So it's very safe. Now, look at the zinc metal plated. This is the zinc metal we plated over 200 cycles. Very dense, no pinholes, no cracks, right? So, and this is actually the platinum plating here is due to the focused ion beam test. You have to put a platinum layer so that you can lift the sample, the specimen. So that's the cross section. Look at how the high quality of zinc we produce here. So, and there are some nice video here. I'm going to show you. This is the pure zinc chloride. You see the bubbles coming out by reacting the electrolyte with zinc, right? And the surface is quite roughened. But if you have lithium chloride added, that helps, right? And further TMACl added, well, that looks good too, right? But still, you can see this asperities on the surface. But if you have our final recipe of everything added with DMC, this is the surface, right? It's not going to produce some dime joint or whiskers or irregular morphology. It's very, very flat. Look at the contrast between these two electrolyte. So when you say, you want to design the anode, most likely you're going to have to design the electrolyte because that's the chemical environment you can tune to vary their properties. Now, if we want to simplify the electrolyte, let's take out lithium and the TMACl, just having zinc chloride plus DMC. So what's going to happen? Well, it's not going to be as desirable as this complex electrolyte. So unfortunately, we have to keep this electrolyte as complex as this way. All right, so now the surface coating, the passivation surface is of a dual layer structure. It's very interesting. The top layer is more organic and the bottom layer is more inorganic. It's like a skin and a covering the bones, right? That's how we passivate ourselves, right? Our skins are passivating us from intruding of water or any solutions, right? So same thing here. We have the organic layer on the surface and the inorganic layer beneath that. So the X-ray photoelectron spectroscopy also proves that when we do the sputtering, the surface is more organic. When you keep sputtering, you remove surface layers, is more inorganic. The practical result. So this is the one of the coin cell result, 4,000 cycles, right? With the NP ratio means actually the capacity ratio between the cathode and between the anode and the cathode. So we have limited zinc. We want to have twice the anode capacity compared to the cathode. Long cycling. So that's the profiles of the cathode. That's after hundreds of cycles, our pod cells is not actually budging, right? That means we don't have a lot of HER formed. This is the pod cell result. And also the electrolyte stays as a liquid at a low temperature. This is going to be very important for storage for low temperature reasons. All right, so to summarize where we are right now. For the anode, right? So we talked about zinc. Now we are reaching 99.95. And because we strengthen the OH bond, we weaken the solvation of hydroxide, we frustrate the solvation, and we use concentrated electrolyte. For iron, we have not touched on this area, but to update you that this is going to be a probably quite a active area in the future. So there are things to work on. And For the cathode side, I didn't have time to talk about the plating of chloride atomic insertion in the metal oxide, but there are activities of vanadium-based and Prussian blue and the metal oxide research. I have to say that vanadium will be expensive, right? That's going to be a challenge. Prussian blue, the capacity is low, and for manganese oxide, that will be the holy grail for aqueous batteries, and there are several approaches to enable it. The electrolyte is the topic for today. We designed a structure of the electrolyte, the solution structure, and we design the energy of water and the solution for the product of hydrogen evolution, which is hydroxide. All right, so this is my group, and so most work was done by Heng and Shang. They have graduated, and these students whose name are marked are the people who are working on aqueous batteries right now. And I want to thank my collaborators and my funding agencies, the Department of Energy and National Science Foundation of the United States. And with this, I really appreciate your attention.
Thank you very much, David. As with all the talks, we're likely going to have lots of questions, and I can see that we've received some already, so I'll move straight onto the Q&A now. So your first question is, besides batteries, what are the other options for energy storage?
Yeah, so right now, besides batteries, so pumped hydro, compressed air, right, capacitors, these technologies are available. But compared to batteries, so pumped hydro and compressed air, they're not modular. That means you cannot put them in a metropolitan environment, right? And for capacitors, the energy density are simply too low, so they're not going to be very competitive to undertake the gigawatt energy storage.
Thank you very much, David. And we have time for perhaps one final question today, which is, why not use NiMH batteries for energy storage?
That's a great question. So the nickel metal hydride batteries have been used for hybrid electric vehicles, right? You might have used one of those, that battery in your hybrid electric vehicles. So the metal hydride here, it's gonna need rare earth element so that you can actually store hydrogen as the hydride form, right? The hydride is hydrogen -1. It's an anion. It has to be stabilized. It turns out that the rare earth elements can do that, but rare earth elements are quite expensive and environmentally costly to mine and refine. That's why that's a limit for this technology to really expand to cover the entire storage market.
Thank you so much, Professor G. Unfortunately, that is all that we have time for today. Any questions that we didn't have time to get to will be sent to the speaker after the event. And as with all the other talks in the event, this talk will now be available to view whenever you want for the next 30 days. That just leaves me to say thank you once again, David, and for everyone watching, we'll be back tomorrow at 8 a.m. Pacific for another fantastic lineup of talks. Goodbye.